Hello, hello.
Yes, sir.
Is class is there?
Class is there, but I think the teacher didn't came.
Maybe anyone can check with Sanjay. Maybe anyone can check with the Sanjay coordinator. Maybe.
Hello. Hello.
Yeah.
Yes, sir.
Yeah. Uh, Good evening.
Good evening, sir.
Yeah. Sorry for joining late.
No issue, sir.
Yeah. Okay. So today, just a second. Which lecture do we have today? Polymer blends and alloys. I'm just opening the PPT. Just a second.
So you have completed the pillars reinforcement and additive spot cluster.
Yes.
You have completed this portion, pillars reinforcement and additive spot cluster.
Which one, sir?
Pillars. Your lecture is today. I think so. Pillars. No?
I have completed polyurethane and epoxies
Okay.
yesterday.
What about pillars reinforcement and additive spot cluster?
I'm not able to hear you clearly, sir.
Pillars reinforcement and additive spot plastic.
Okay. Yeah. That I will cover in the next section, sir.
Okay.
Yeah.
Not
Today I
really.
will continue with the polymer blends and alloys.
Okay.
So for additives part, I will cover it in the next session.
Okay. That's it. Okay, sir. Thank you, sir.
Okay. Yeah. Okay. So I am just sharing the screen. Okay. So today we will be talking about polymer blends, alloys, and composites. Okay. Yesterday we have talked about polyurethanes and epoxy, as most of your part of the into the polymer has been streamlined, and you have been gone through most of the polymers. So now I think it is okay to talk about the different polymer blends, alloys, and what are the composites. Okay. And after talking about blends, alloys, and composites, then we can have an idea about what are different additives and which additives can be used for which polymer systems. Okay. So just begin with this polymer blends and alloys. Now, actually, what is polymer blend? Now, polymer blend is nothing but a mixture of two different polymers. Okay. Just, huh. Polymer blend is nothing but a mixture of two different polymers, such as mixture of polyethylene and polypropylene. We can call this as the blends of polyolefin, or blend mixture of polycarbonate and ABS. We can call it as a PC ABS blend. Okay, so it is nothing but a mixture of two different polymers. Okay, so that mixture is a homogeneous mixture. Okay, and it is also thermodynamically stable mixture. Okay, so talking about thermodynamically mixture, thermodynamically stable means the whatever the entropy of the system is, or the Gibbs free energy of mixing of the system is, it is less than zero. Okay, so just to brief you about what is the thermodynamically stable mixture. Now let's talk about actually what happens when you mix two different polymers. Okay, now just tell me, when you mix polyethylene and polypropylene, as here it is shown in this figure, so what do you think? Will it mix properly like sugar and water, or will it mix like oil and water? What do you think? Yes, I want answer. What do you think? Whether it is possible to mix polyethylene and polypropylene? And if we mix it, what kind of mixture we will get? Whether the mixture will be like dissolving sugar in water, or like dissolving oil in water? How will be the mixture? What do you think? Am I audible?
Sir, you are audible, but I don't think anyone knows the answer, so you can proceed.
Okay, fine. So basically, when you mix polyethylene and polypropylene, now you might wonder that these two polymers, as they are having this same kind of structure, so having same kind of structure might help this polymers mix well together with each other. Okay, but this actually is not the case. When you mix polyethylene and polypropylene, a phase separation occurs, like you can see in case of oil and water. Okay, so such kind of phase separation, it is generally due to the uh, increasing entropy. Okay, or due to the order of the entropy. So entropy is nothing but the random orientation of the molecules, in simple way, if we can say. Okay, as you can see here in the picture, these are solid particles, liquid, and then gas. So the order of randomness is increasing as we move from solid to gas state. So that means the entropy is increasing. So likewise, this was just to give you an idea about entropy. So thermodynamically stable mixture means the system whose entropy is low, and the mixture which is homogeneous. So when you mix two different polymers, it will be a homogeneous mixture with low entropy. So you will get a single phase of the polymer blend. You will not see a phase separated blend. Okay, and when we talk about polymeric alloy, so polymeric alloy is nothing but incompatible polymeric blend. Okay, which require third phase to acquire homogeneous and thermodynamically stable structure. Okay, so blends, when you mix both two different blends together, they can be either compatible or incompatible. Okay, so if they are incompatible, you can go for compatibilization. So for compatibilization, we add a third molecule or third phase which makes the homogeneous mixture and thermodynamically stable structure. Now, concepts of blending, why blending is required. So blending of two different polymers, it is generally required to develop a tailor-made material, generally to acquire synergic effect in the base polymer. So synergic effect means if you are using, for example, polycarbonate along with, or you are using polystyrene along with ABS, okay, acrylonitrile butadiene styrene. So what happens? Polystyrene is a brittle material. So when you mix it with ABS, ABS material has elastomeric component in it. So due to which it increases the impact strength of the polystyrene material, or it reduces or lowers the brittleness of the polystyrene material. So the base material is polystyrene, and the synergistic effect, it is generally gained by mixing it with ABS. Then again, to develop cost-effective macromolecules for modern applications. That means when you mix two different polymers, you generally go on cost cuttings. Okay. For example, here in this diagram, you can see you can mix commodity polymer with engineered polymers. So basically, engineered polymers are costly as compared to the commodity one. So when you mix with the commodity one, you can also increase the properties of both the polymers, and also you can lower down the, or you can work on the cost reduction of these engineered polymers. Okay, so mixing polyethylene terephthalate with HDP or PP might lower your cost. Okay, then again, you can also mix these engineered polymers with high performance polymer like liquid crystal polymers or polyether ether ketone or polyvinylidene fluoride. Okay, so or you can either mix high performance polymers with commodity polymers also. So blending results can be achieved by combining different polymers, or we can say interclass polymers like commodity, engineered, and high performance. Now, just to give you a glimpse about why blending is required actually. So blending is generally required to extend the engineering resin performance by diluting it with low-cost commodity polymer. So as we have seen the example of one of the engineering polymer like polycarbonate. So if you can reduce the performance or you can reduce the cost by blending it with the commodity polymer such as PPP, okay, or polystyrene. Then to develop materials with a full set of desired properties. So like if there are materials which have certain properties or which compromise on certain properties. So to just enhance those properties, we can mix with another material so that we can get a full set of desired properties. For example, impact strength, rigidity, ductility, chemical resistance, abrasion resistance. Okay. Then to improve processability. Again, there are few
Sir,
polymers.
so just
Yes.
sorry to interrupt. The first point, the definition, which is saying that to extend engineering racing performance by diluting it with low cost polymers. So, don't you think that engineering resins are already developed due to their performance or used for their performance? So, when we are diluting it with the low cost polymer, are we enhancing further, performance of the engineering resin, or we are just diluting it to have a low cost product with
We are
the
just
good
diluting it. Yes, we are just diluting it to have a low cost product or for the cost reduction purpose. So where these properties, like if you see in automotive, okay, so in case of automotives, there are some parts which are required on the exterior side. Okay, so for exterior parts, we cannot compromise on the properties or we cannot dilute the performance of engineering resin, right? But in case of interiors, where engineering polymers are being used, in that case, we can dilute some of the performance of engineering resins. Okay, so that
While,
cost reduction can be
but
achieved.
interior is also more important, right? Because driver is sitting, he's observing that perceived quality point of view.
Yes, driver is observing. So we can, so diluting performance, it doesn't mean that diluting performance in every aspect. Okay, so
No,
from
but
interior,
we have mentioned extend engineering racing performance. So my question is, by diluting it with a low cost polymer, are we extending the performance, or are we, decreasing the performance and to have a, low cost product?
no, we are actually extending the performance, but in what case we are extending, we are just reducing it on the cost basis by mixing it. See here, diluting is just blending it with low cost or commodity polymer.
Okay.
So then to improve processability, so processability, there are some certain polymers which are difficult to process. Okay, so these polymers can again be blended with some uh, like temperature polymers, or we can say low processing temperature polymers, so that they can its processability can be improved. Then to utilize the scrap generated at various steps. Now, for example, there are some post-consumer recyclers. So these post-consumer recyclers can be blended with the virgin polymers, or it can be blended with some another material. Then to get a high performance blend from synergistically interacting polymers. So again, there are subsystems in which you use two different polymers. So finally, what you will get is the synergistic performance of two different polymers. So synergistic performance means you will have the properties of both the polymers at an enhanced level. Okay. As the polymers would have given the properties or would have exhibited the properties individually. So it would be better than the individual properties. So to again to achieve the customer specifications in a product. So as per the customer specifications or customer requirements, you can go for blending a product to achieve the certain desired performance. And you can also obviously have reduced R&D expenses and the time which is being consumed in developing new monomers and polymers to yield the similar performance. Okay, so from starting from scratch and then going on developing the different kind of new molecules, no new materials with the different set of properties. So it is a rather expensive process also. So to reduce these processes or cut the R&D cost, generally blending is also being carried out. Then quick formulation changes like which can give the plant flexibility and high productivity to the material. And blending, it reduces the number of grades that needs to be manufactured and stored, therefore saving space and capital investment. So as we have seen, there are different grades of materials available in the market for same polymer. So those grades, each grade have different set of properties and different application area to serve in. So to reduce such kind of grades, generally blending can also be carried out. Then lower capital expense, which is generally involved with scale up and commercialization. Now, there are some criterias for blends, like we can say rheological criteria and interfacial criteria. So rheological criteria is nothing but the flow criteria, we can say, or the viscosity, the term which is being associated with the viscosity of the materials. So for rheological criteria, we can say that the polymers which are going to be mixed together, it should have a similar range of viscosity. And the polymer chains which undergoes the blending, it should have a sliding effect. Okay, the different polymer chains should slide along each other. Then talking about interfacial criteria, when two different polymers are being mixed, it should have a positive spreading coefficient at interface. So interface is nothing but the boundary at which two different polymers are interacting. Okay, and at that boundary, these polymers, they should have a positive spreading coefficient. Positive spreading coefficient means it should wet along the interface, or it should spread along the interface uniformly. Just to give you a simple example, if you put a drop of water on the piece of paper, the drop of water will completely wet the paper. Okay, so that means it is having a positive spreading coefficient. Now, if you take the same case with the lotus leaf, so that drop of water, it will not completely wet the lotus leaf. It will just roll off the surface. So that means it is not, the lotus leaf is not having a positive spreading coefficient. Okay. Then higher chain interaction ability at interface. Now, talking about interface again. So at the interface or at the boundary, two different polymer chains should interact positively along with each other. Okay. Okay. So overall, this we talk about the criteria. So viscosity, the synergistic effect, and the thermal transition. So when we talk about viscosity and thermal transition, so these blends, they are miscible polymeric blends, and they are miscible at all temperatures, but at a certain concentration. That means if you are trying to mix a PP-ABS blend, okay, so now you are having 30% polypropylene and 70% ABS. So at 30% PP and 70% ABS, your blend will be miscible, okay, at all temperatures and at this concentration only. But as you increase or decrease the concentration of any of the polymer, your blend, it will move towards the immiscibility. Okay. Then you have this thermal transition and synergy, where you will find immiscible polymeric blends. That means they are at all temperatures and at all concentrations, they are immiscible. Again, you have this region where viscosities, you can get a viscosity, synergistic effect, and a thermal transition. And in this region, you will see a miscible polymeric blends, which are miscible at all temperatures and at all compositions. Whereas in this region of viscosity and synergy, you will have a miscible polymeric blends, which are miscible at any composition, but at a certain temperature. That means, again, talking about PP-ABS. So let's say you have PP-ABS. So at any concentration, your PP and ABS, it will be miscible. Okay, but it will be miscible only at 30 degrees Celsius temperature. Okay, let's say for example. So as you increase or decrease the temperature, so your blends will move towards the immiscibility region. Now, talking about miscibility, immiscibility, compatibility, incompatibility. So generally, when we mix two different types of blends, either they will be miscible or immiscible, or we can say compatible or incompatible. Okay, so if they are incompatible, okay, so miscibility and compatibility, both are these two different terms. They might look similar. Miscibility is the homogeneity which is achieved at a molecular level, but compatibility means whether the you can say two different blends, if they are compatible with each other, they can have good properties, okay, even though they are immiscible. But if they are miscible and they are not compatible with each other, their properties might get affected. So this is the difference between compatibility and miscibility. So if there are certain blends which are incompatible, so to make them compatible, generally we add a third phase, or we can say third molecule, which has chemistry to make two different materials or two different polymers compatible. So this process we call it as a compatibilization. So compatibilization in polymer chemistry is the addition of a substance to an immiscible blend of polymers that will increase the stability. So if you see this region, see this is the polymer A, this is polymer B. Okay, so these are the schematic representations for diblock, triblock, multi-grafting, and single grafting polymers, which are at the interface of a heterogeneous polymer blend. Okay, so these polymers they can act in this way to make two different polymers compatible. So see, this is the example of PP and PBT, polybutylene terephthalate. So this region with green color you have polypropylene. This with pink color you have polybutylene terephthalate. So along the interface you have these molecules. Now for the compatibilized system you have PP and you have PBT. Okay, and in between you have this B molecule. Okay, this B. So this is nothing but a compatibilizer, which is compatibilizing this both the blends. So how it is being compatibilizing? By such a triblock type of copolymers. Okay, by acting along the interface. Okay, so this is the interface of the two different polymers. Now there are different strategies of compatibilization. Like first is the addition of a small quantity of third component that either is miscible with both the phases, a co-solvent can be added, or you can add a large quantity, basically less than 35%, a core shell copolymer, okay, which behaves like a multi-purpose compatibilizer cum impact modifier, okay, or you can go for a reactive compatibilization. So for reactive compatibilization, the different interactions are being induced between polymer A and polymer B by creating the chemical bonds between the two different polymers, either during compounding or during the forming process. Or you can have a mechanochemical blending, means like, or you can say in situ reactive compatibilization type. So that can lead to first chain breakage and then again recombination of those chains, again which can generate a copolymer. So this copolymer again it will compatibilize two different polymers. Now talking about the classification of blends. On the basis of miscibility, we have this miscible blends or immiscible blends. Okay, so for miscible blends, we have when the free energy of mixing is less than 0 for delta G, we call it as a miscible blends, or the blends will be miscible. And when the delta G or free energy of mixing will be greater than 0, you will have immiscible blends. Okay. So for immiscible blends, you have again three different chemistries like compatible blend, semi-compatible blends, and incompatible blend. So for compatible blend, you have delta G again, which will be less than 0. So in this case, we generally add a third phase and solubility is being achieved at all compositions and at all temperatures. For semi-compatible blends, the delta G is less than 0. Okay, and for this, solubility is achieved at certain composition and certain temperature. And for incompatible blends, again the delta G is greater than 0, where you will have no solubility at all composition and temperatures. So these are the types of miscible blends or the morphology which can be achieved. So first one, we call it as a spherical blend morphology. Okay. And for this, we have a delta G, which is less than 0, where we have a polymer A with high molecular weight. And this system, it forms a spherical blend morphology. In the next picture, you can see this kind of morphology. We call it as a dispersed blend morphology. Okay, where polymers with same chain interacts with each other. So this white part is polymer A and black part is polymer B. Again, if you go towards the next picture, it is a co-continuous blend morphology. So in this co-continuous blend morphology, now this is the reverse case as compared to this one. Here the polymer A was high molecular weight and polymer B, which is black one, was a low molecular weight. Now in this case, the polymer B is with high molecular weight, and as the dispersion is getting converted into the co-continuous blend morphology. Now methods of blending. Now there are different methods of blending. First is mechanical mixing. So this mechanical mixing is the cheapest one. Another is dissolution in co-solvent. Okay, you have a solvent system and then you add a co-solvent and then you transfer that system into the mold where you cast that solution as a film and you just freeze or spray dry it. Then latex blending, fine powders mixing, and again the use of monomer as a solvent for another component, and then polymerizing it. So this technique, we call it as an interpenetrating polymeric network. So interpenetrating polymeric network are just materials with interlaces, or you can see general example which I can give you is the shoelaces, how your shoelaces are being interlaced with each other. So that kind of structure is being formed, which we call it as an interpenetrating network. Okay. So talking about methods of blending, melt blending. In melt blending, we mix two different polymers in molten state and under the action of shear. Okay. And in this technique, thermal degradation does not occur at processing temperature. So for this technique, we can use either an extruder, which can be a single screw or twin screw extruder, or we can have a planetary roller extruder. Okay, in which there are 6 or more evenly spaced planetary screws which revolve. Okay, so in extruder you have this material plastic powder coming through this hopper. Okay, and as the screw is getting rotated, the material is getting mixed, conveyed, and coming out of the die. Okay, so blends which can be prepared by melt technique. Some of the examples are polypropylene and polyamide. So this PP polyamide blend, they decrease the water absorption of polyamide, improve the processability of polypropylene. Okay. For PP-ABS blending process, 70% PP and 30% ABS. They are generally blended at elevated temperature in extruders. Okay, and these blends, they generally can have good fluidity, rigidity, low shrinkage, and coating. Advantages are liquid or dispersion agent can get eliminated. This process reduces the cost which is associated with the solvent process in case of solvent casting. Then it again reduces the contamination in the blend. Disadvantages are due to the presence of the extruder and motors and rotating screws, high energy consumption is being required. Then as the application of temperature is there, higher temperatures are employed. So due to which degradation of either one or both polymers might occur. Okay, so we can just control these things. Again, cross-linking. So again, if you are trying to use certain different materials or initiators into your blend, so it might create or it might generate a cross-linking reaction in the extruder, or it can certainly create a free radicals in your blends, which can lead to a grafting process or graft formation. Or again, due to the action of heat, chain scission reactions might occur, again leading to the degradation of the one or both the polymers. Okay. So in solution blending, generally for solution blending, you have two different polymers, polymer A and polymer B. So you dissolve these polymers in common solvent, you stir it, and you again, after stirring it, you mix it. Okay. And this solution or this polymer blend solution, it is again just uh, casted onto a substrate, or we can say a mold, and due to the action of the solvent evaporation, films are being or the solution, it turns into the formation of the film. Okay. Or generally membranes are also being generated. So example is polysulfone blend with polyvinyl pyrrolidine. Advantages are rapid mixing. Again, it requires low energy consumption, whereas for extruder or for melt blending, there was higher energy consumption. Then here degradation by heat and shear are minimized. Here unfavorable chemical reactions are also avoided. Disadvantages are that the consumption of solvent is very much high. And if you see commercially, this technique is non-viable. Then latex blending. So again, here two different polymers which are available in the latex form, they are mixed, and after mixing, they are just dried and coagulated. Okay. So the example, emulsion polymerization of rubber or thermoplastic acrylates are the raw materials which can be given example of for latex blending. So for this process, spray drying is most frequently used method, and the morphology which we can get is the fine dispersion of molecules, like the drop diameter from 100 to 200. Okay, and these blends, they can be directly used as an example of paints, adhesives, or as sealants. Okay, and advantages are, it is least, which minimizes problems of incomplete mixing, chemical changes which are caused by heat and shear. Disadvantages consist of adding emulsifiers for stabilizing the mixtures. Then residuals of initiators are being left as the residues. Chain transfer agents, stabilizers, they are also being left as the residues. And then due to this, all these issues, main problem is the high content of contaminations. Okay. Now talking about the different properties and application of polymer blends and alloys. I will discuss different polymer blends, its application and its properties, and what are the its alloys. Okay. Now, as we have talked, polymer blends, it can be commodity polymer blends, engineering plastic blends, or specialty plastic blend. So when we see this commodity polymer blends, in this, either both polymers should be from commodity class. Okay. When we call it as the engineering plastic blends, any one of the polymer we should be from engineering class. And for specialty plastic blends, any one of the polymers should be from spatulate class. So talking about polyolefin blends. Now polyolefin blends means I'm talking about polyethylene based blends. So polyethylene based blends, they have good flexibility, good tensile strength, and dimensional stability. And it also has good heat sealing nature with lower melting point. And these blends also have good recyclability and good hingeability. So when we talk about hinging properties, so hinging properties are the inherent properties which are being contributed by the polypropylene based blends. So polypropylene has good hinge properties due to the uh, presence of the polypropylene material. Good hingeability can be achieved for the polyolefin type blends. And these blends, they can, due to its inert nature, they can be used in food acids and base packaging, as they have this good, excellent voltage cracking resistance. So, or we can say insulation properties. These PE PVC blend can be used in the sheathing. So this black cover, we call it as the sheath of the cables. In this case, PE PVC blends are also being used. Whereas to achieve an excellent solvent resistance, generally polyethylene is cross-linked and it is blending with ultra high molecular weight polyethylene. So by blending, you can have a material which acts as a higher solvent resistance and which can be used in the fuel tank applications. So now talking about polypropylene based blends. Now when we see the polypropylene based blends, again the properties are somewhat similar to the polyethylene based blends. Okay, again you have this good ability, hot fillability. Okay, but you can have you will have poor printability. So polypropylenes, mostly polyolefins. So in this case, polypropylene surface energy is very much low. Okay, so due to the uh, it is very much high. So due to the high surface energy, these materials, they have poor printability. Okay, means if you go for printing something on the polypropylene material, you won't be able to print it properly. Okay, so such kind of disadvantage might occur in case of polypropylene based blends. And these PP blends, they are mixed with EPDM, ethylene propylene diamonomer, to achieve excellent toughness, and due to which it can be again used in the automotive dashboards. So for PP NBR, for NBR blends, they offer high resistance to pressure burst, and therefore it can be used in the pipe fittings. Now, when polypropylene is mixed with ethylene vinyl acetate, okay, so it can have a good tribological properties. Tribological properties means frictional properties. It will have good frictional properties, and due to the higher friction properties, these materials can be used in manufacturing of the synthetic floor for basketball. Then vinyl blends. For vinyl blends, generally PVC based, these vinyl blends, they are susceptible to thermal degradation because vinyl blends, they are heat sensitive materials, but they can give you fair impact properties. They can give you good insulating nature, and due to the presence of the chlorine molecule in the vinyl blends, it can give you the flame retardancy. Okay, and these PVC based blends or vinyl blends, they are generally mixed with NBR, nitrile butadiene and rubber. So these NBR blends, they shows thermal insulation, and therefore it is used as a solar insulating tubing. Then for PVC PP, It again gives good tripological properties, and therefore can be used in floor laminates. In case of automotive applications, PVC is blended with acrylics to have good abrasion resistance, and therefore it can be used under the underbody of the automobiles. Then styrenic blends. Now, as in the previous discussion, we have talked about the styrene being a brittle material. So here, if you see, excellent impact resistance can be achieved in case of styrenic blends when incorporating it with ABS. Okay, or while making a copolymer of styrene, like blending it with acrylonitrile and butadiene. So such kind of ABS will give you excellent impact resistance, and it will be a thermally stable in nature, okay, and optically clear except elastomeric combination. So if you see polystyrene, if it is blended with elastomeric component, for example ABS or EPDM, so in such case the optical clarity of the material will not be there. Now to achieve an optically clear material, you need to blend it with some another material, another polymer except the elastomeric one. So in case of styrenic blends, so as they have high optical clarity, they are generally used in light diffusion for as a light diffuser bulbs, and polystyrene when blended with again polyethylene, they have high specific strength, therefore can be used as a packaging material. Okay. Then polystyrene PVC blended can be done to achieve a good thread stability in blood sample bottle collections. So thread stability of some of the materials is poor. So to give it or the threads get wear and tear. Okay, due to the action of wear and tear, they get worn out. So to avoid it, generally polystyrene is blended with PVC to achieve a good thread stability. Then talking about polyester blends, polyethylene terephthalate, polybutylene terephthalate. Okay, so basically these two are most commonly available polyester blends. When we talk about these polyester blends, these blends can give you good barrier properties and a optically clear material. Now, these blends when blended with PP, it can show you good optical properties which can be used for solar applications. Or when PET is blended with polycarbonate or PBT is blended with polycarbonate, so due to the high voltage crack resistance, this material can be used as starter in electrical devices. Okay. Again, PET, PVC, they have good tribological properties and good surface finish, and therefore they can be used in the seat making of the automobiles. Talking about polycarbonate blends, they have these thermal properties, mechanical properties. Okay, so in case of mechanical properties, polycarbonate blends can give you good impact resistance, notch sensitivity of the polycarbonate. It is generally eliminated by blending it with some other polymers. And when we talk about the clarity, polycarbonates are optically clear material and they exhibit excellent noise reflection. Okay. So therefore, polycarbonate when blended with ABS, it can give you good impact resistance. Therefore, it is used in the casing of electronic devices. And polycarbonate when blended with polytetrafluoroethylene, it can have self-cleaning properties with good dimensional stabilities. So these can be used in the gears of the photocopy machine. Again, polycarbonate and PMMA blends, they have good optical clarity and good piezoelectric properties. So therefore, they can be used in touchscreen panels. Now, polyamide blends. Now, these polyamide blends are the blends which are having the base polymer as a nylon. So, such kind of polymers, they are generally, or such kind of blends, they are generally like having a good impact strength. Okay, or we can see these mechanical properties. These have good tensile strength, excellent reinforcing nature. Okay, and you can just add some another reinforcing agent, can blend good well with the matrix, then it sustain high application temperature. And as we have also or we are also aware that the polyamide blends, they are hygroscopic in nature. So this hydrophilicity or hygroscopicity can be eliminated through blending. So basically nylon when blended with polyethylene or polypropylene, they have good barrier properties with heat sealing ability. Again, nylon when blended with polyethylene terephthalate, they give excellent mechanical properties and can have self-assembling structure. Like for example, seat belts, which are being used in the car. Then nylon NBR blend, they have good abrasion resistance. Therefore, they can be used in slitting gloves. Now coming towards the elastomeric blends. So elastomeric blends are the blends which have one of the elastomeric components with the another polymer. So these blends, they have good oil resistance as they are the elastomeric components, and they have good electrical insulation, and their crazing properties or the thermal crazing is very low. And when we talk about mechanical properties are excellent. Okay, so it has good very good flexibility, elastomeric blends. So as you can see, the examples of ABS PP blend, they are a good choice for the suitcase as they give one high impact strength. So again, polyphenol oxide when blended with ABS, they offer good dimensional stability and good impact properties. Again, when talking about ABS and nylon, so these materials have good acoustic amplification and therefore they can be used in the stethoscope diaphragm. Then polysulfide blends. So the mechanical properties are good. For example, the tensile and flexural strength. Rigidity of these polysulfide blends is high. Dimensional stability are high, and thermal stability is also high. Talking about the adhesive properties, polysulfide blends, they generally have good adhesive properties. Therefore, when these polysulfide are mixed with epoxy type of blends, epoxy type of materials, so they offer good dimensional stability and therefore are used in the impression applications for in the dentistry, as you can see in this picture. Again, polysulfide and PVC, they possess good adhesion with polymeric and non-polymeric materials or substrates, we can say, and therefore they are also used in sealant applications. Then polyimide blends. Now these polyimide blends, they have high thermal stability with high chemical resistance, and due to its semiconducting nature, okay, these polyamides blends are used in thin film semiconductors. And these blends, when blended with elastomers, they show good thermal conductivity. That's widely used in film meters for Peltier plates, as you can see in this picture. Now, this polyamide, when blended with PTFE, again it has self-cleaning properties and therefore these can be used in the membrane applications also. Now talking about the composites, as you have seen, alloys, blends and alloys, they are the binary material. Again, composites, they are also one of the binary material. So the difference between both the blends is between blends and composites is that blends is the single phase, physically mixed material. Just a second. So blends is a physical material or is a binary material, and composite is also a binary material, and this material, they are distinguished based on their phases. So one is single phase, another is multi-phase. One is physically mixed, again second is also physically mixed. So when you see at the composite structure is nothing but one component you have a reinforcement component, another component you have a matrix component. So when you mix matrix and reinforcement, you get a composite one. So now there are also another composites which you call it as a green composite. So these green composites are nothing but a matrix along with reinforcement, and these can be natural one, and when natural resin and natural fiber is being used, the composite which we get is, we call it as a green composite. Okay, so either resin can be natural or fibers can be natural. Okay, any of the components should be a natural one. Now in case of biocomposites, we need both the components natural. Okay, we need resin also natural and fiber also natural. For example, for green composites, you can use in case of resin, you can have epoxy resin, which is a synthetic resin, and for natural fibers, you can have fibers which are taken from this coir fiber, or it can be plant fiber or any fiber available from the nature.
What is coir fiber?
Coir fiber, coir is the material which is the casing of this coconut. Okay, so from that casing or covering of the coconut.
Okay, that coir.
Yes, that is coir. So examples of naturally occurring green composite, just to give you an example what actually is a composite. So banana fruit, it is one of the naturally occurring green composite which have
sorry to interrupt. There is one more vegetable, right? That through that also we are making a fiber and natural,
which vegetable?
like which you are using for that bathing also.
Yes,
That
loofah.
all.
Loofah.
Okay.
Loofah, it is a plant extract. So loofah fibers are also there. They are also strong reinforcement.
Basically, it's a vegetable, but after when you are soaking that, then we can get it. Yeah, kind of a. Yeah.
Okay. So coming to the naturally occurring green composites, banana fruit. So banana fruit, they have fibers which are reinforced in the protein matrix. Banana leaf, they are composites of fibers and phytochemicals. Then in case of animals, we have conch or shell, which are examples of reinforced ceramic composites. When we talk about deer horns, they are the excellent examples of tissue, bone, or reinforced composites. Okay. Now, why do we need to move towards the green composites? Now, till now we have talked about the. I've just given you an idea about the composites in general sense. So composites are nothing but a matrix or polymeric matrix in which you have a polymeric resin, and in that polymeric resin you have a reinforcement. For example, epoxy resin is there or polyester resin is there, and in polyester resin you have glass fibers laid out. You have one layer of epoxy resin, you have another layer of glass fibers, again one layer of epoxy resin, another layer of glass fibers. So you have some defined number of layers, and this material can give you a composite material. So this is a synthetic material. So now, due to the some environmental regulations, most there are also a possible viability of producing green composites, so which have sustainable properties which can survive without harming the environment. So these green composites, they can also be durable, have excellent specific strength, aesthetic properties, recyclability, and they are ecological alternative. Now, examples of man-made green composites, we can say this Mongolian bow, okay, which is made up of wood horn and sinew composite. Then sitar from the 18th century, we can say it is a base, its base is wood and shellac. Shellac is again one polymer, naturally occurring polymer, and its neck, this neck is made up of gold threads and ivory, which is being reinforced with threads and silk. Okay. Now this, if you talk about this furnitures, so this is made up from synthetic one, which is epoxy or unsaturated polyester resin, and this is being mixed with wood fiber or floor as the reinforcement. So again, these floor mats, they are nothing but PVC matrix, which is being added with banana fiber reinforcements. Now, classification of composites on the basis of matrix and on the basis of reinforcement, we can classify the composites. So composites can either be thermoplastic or thermosetting, okay, based on the matrix. And on the basis of reinforcement, they can be non-wood natural fibers or wood fibers. So non-wood, when we talk about non-wood natural fibers, they can be plant-based fibers like straw fibers, grass fibers, seeds. And in case of wood fibers, they can be recycled fibers or soft and hard woods, okay, which are rich with lignin and cellulose. So on the basis of resins, thermoplast or the matrix, we generally have thermoplastics like polylactic acid, polyhydroxybutyrates, cellulose acetate, starch, biodegradable polyurethane. Okay. And for thermosettings, you have epoxy from renewable resources, like vegetable oils are being used to manufacture epoxy, or polyalkaline dicarboxylates are one of the thermosetting examples. And these are not limited to the matrix process. These are thermally stable composites having good mechanical properties. Now, on the basis of bio-based fibers, okay, again, these can be non-wood natural fibers and wood fibers. So when we call it as non-wood natural fibers, we have straw fibers, bast, okay, then leaf, seed fruits, grass fibers. So examples of straw fibers are like rice, wheat, corn, and straws. For bast, we have kenaf, flax, jute, or hemp. For leaf, you can have sisal, pineapple, leaf fiber. When we talk about seeds or fruits, we have cotton, coir, coconut. When we talk about grass fibers, we have bamboo fiber, switchgrass, elephant grass, and wood fibers, we have soft and hardwoods. And in case of recycled one, we have newspapers, magazines, magazine fibers. So these materials, they add flexibility in the composite. They provide strength to the composite. They provide, you can say, uh, the overall mechanical strength to the composite. And along with it, they also reduce the cost of the material. So basically, composites, we can say, they are important because they have high strength to weight ratio. Means they have, with low weight, they have a higher strength. So there are different processes for manufacturing of composites. So one can be open mold process or closed mold process, filament binding, or pultrusion. So pultrusion is nothing but similar to extrusion process. Open mold process consists of laying matrix and reinforcement into shape in a open mold. In closed mold process, you have a mold which is generally closed, and after closing, the composite is being formed. Filament binding, you have a continuous filament coming out of the machine, and it is just out, while coming out of the machine, it is being dipped in the resin and wrapped around a particular shape. So we will discuss these techniques one by one. So see, this is the hand layup method in which you have a mold first, which is being treated with a mold release agent, and then a thin gel coat or thin resin is being applied on the surface of the molding. And when the gel or coat is being partially set, these layer of resins and fibers, they are being applied. Okay. And these fibers, they can be in the form of mat or cloth, and each layer, it is being rolled so that it can impregnate the fiber with resin. Okay. And any unnecessary voids or gaps can be eliminated. Then in the fourth stage, the part is being left to cure. And after curing, in the fifth stage, the fully cured part is being removed from the mold. So this is the simple hand layup method.
What about that hardener we are adding for curing purpose?
Yes, hardener is also being added with this
Which,
method.
which stage we are adding?
In while coating stage also, coating stage only, when the resin is applied, no? At
But
that stage only, yeah, the mixture is being
first
mixed
you
with the
mentioned,
hardener. Yes,
but first we are adding a release agent, right? So that part will come
resin, it
from
is
without.
generally, see, as we have discussed in the yesterday's class also, the systems can be one component or two component. So more in case of one component system, you have this resin and hardener mixed together, okay, at a specific temperature. So while applying, you apply the resin first onto the mold, right? Then you lay over the fibers in the form of mat or cloth, and you press. Again, you apply the resin. Again, you press. Okay. When this process is over, you just leave the part for curing. So this is the curing process. Now, during this curing process, you will either apply the temperature. Okay, mostly temperature is applied. So due to the application of temperature, here your resin, it gets cured or cross-linked. Here your hardener and the
I
resin,
think
it reacts.
I think before 4 we are adding hardener for hand layer process.
Where
Before fourth process we are adding that hardener for curing purpose, self curing.
before, see, in some cases it is being added, but in most of the cases, what is being done, one component system is being used. Okay, so in one component system, you have epoxy or you have resin and hardener mixed together. So it will be cured only when you apply a specific temperature. So for
That
during mix,
that will be a comes under compression molding, that you are giving heat SMC sheet molded composite maybe. But for hand layers,
yes, in compression you have different type, different thing,
yeah,
different process.
But for hand layup, I think we are adding that hardener that layer kind of. It's a liquid kind of, but
Yes, it is a liquid
reaction
kind of process.
through reaction it becoming hardened. Yeah. Okay.
Then spray layup method. So now in this spray layup method, again the difference between the spray layup and hand layup is nothing but in this spray layup process, you have a spray gun where the fibers are mounted on the spray gun and or the rover is mounted, fiber rover, and the fiber it is being extruded or it is being expelled through the spray gun, chopped and sprayed onto this resin. Okay. So chopped fibers and resins, they are generally simultaneously sprayed onto this mold. And applications of this spray layer process are lightly loaded structural panels like truck fairings or bathtubs, small boats. Okay. Now, this is the cold mold, closed mold process. Now, in closed mold process, you have see here you have these three different process like injection molding, injection molding, compression, and transfer molding. Okay. Now, in this type of processes, you generally have a preform in molds which consist of two sections that open and close during each cycle. Okay. And as you compare it with spray layup and hand layup, the tooling cost for the closed mold processes is twice the cost of the comparable of open mold process. Advantages are it can give you a good surface finish, higher production rates are possible, and close control over tolerances is being possible. Then you have filament winding. In case of filament winding, again you have different rovings which are being pulled through the tensioner and which are being dipped into the resin bath. And after being dipped into resin bath, they are being wounded up onto the rotating mandrel, or we can say a drum roller. Okay, and this is a highly automated process. It has low manufacturing cost and high throughput. Pultrusion process is nothing but similar to the extrusion process where you have a continuous fiber roving which is dipped into the resin bath and it is coming continuously out of a shaping die. Okay, so these are some of the examples of the uh, composites which are being produced using the pultrusion product. This is the pultrusion process where you have this krill or rovings and it is being dipped into this resin bath and then it is being extruded or pultruded through this free die former and then die. Then it is being extruded on through the pull rollers. Okay, in the straight sections as mentioned in this picture. Okay, so advantages. These are some sustainable technologies which can be easy to process. Durable composites are being manufactured. Less carbon footprint. These mechanical properties have superior in case of composites. As I have mentioned, the composites have higher strength to weight ratio, and these are the eco-friendly solutions. Disadvantages are they have low fire resistance. So these can be the fire resistance can be overcome by adding flame retardant additives. Poor interface adhesion, and therefore it can require modification. So the interface of the fibers and resins can be poor, and therefore some due to some modification, it can also be achieved. High moisture absorption. Moist composites again they are prone to absorb moisture and high shrinkage tolerance required. Applications are in case of automotives, in case of defense applications. Okay, so for example, DuPont has some marine composite with Kevlar, which is useful to provide ideal balance of strength, stiffness, and lightweight properties for many marine applications. Okay. Then again, talking about the natural example of KNF fiber reinforced composite, which is alternative to bio composite material, which is generally used for the construction applications. Then in wood fiber composites, in case of furniture, cellulose and PTFE matrix in case of biomedical applications. Okay, so that's all about the composites. If you have any doubt, you can just ask.
So this slide, can you please share?
What slide? You are talking about slide?
That yeah, which you presented, yeah.
Yes. I will be surely sharing it with Sandeep, sir. Sandeep sir will share it with you.
Okay.
Yeah. Okay. So if you have no doubt, so Sandeep sir, can we stop them here? I'm done with the lecture. Hello, Sandeep sir? Okay, I think Sandeep sir is not available. So I think we can stop here.
Tomorrow,
So,
which topic we are going to cover?
Tomorrow 30, right?
Yeah.
Sorry. Yeah, please.
I will just talk with Sandeep sir about tomorrow's schedule, and then Sandeep sir will convey you the message about
Okay.
tomorrow's schedule.
Okay.
Hello. Good evening, sir.
Hello.
Hello.
Good evening,
Good
sir.
evening, sir. Please. Anything else, sir? Hello.
Yes, sir. Yes.
Please, sir. Please, sir.
Yes, sir. I'm done with lecture, sir. Today's lecture.
Okay. Yeah, okay.
Okay, sir.
What about tomorrow?
Tomorrow I will inform you, sir, in the morning.
Okay. Maybe
Yes, sir.
Pawan is there, no?
Yes, sir.
Pawan is there, no?
Yes.
Okay, okay. Okay, sir.
Okay, sir. Okay. Yeah. Thank you, sir.